you very much for the invitation. It's a little bit weird for me to give an English talk here at Technical University of Crete. Actually, this is the 9th year working here, and this is the first time speaking in English, giving a talk in English to our students. So I'm going to talk about Backscatter radio. Everyone and each of you has extensively used Backscatter radio in your daily life. Probably you don't know it, but you have used Backscatter radio, and you're gonna understand how that happened, how that has happened. And this is the outline, this is the agenda of my talk. I'm gonna show you the basic principles of scatter radio communications. Talk a little bit about the innovation that we have proposed. If we have time, I'm going to also talk a little bit about energy harvesting, which is complementary technology to Backscatter radio. And finally conclude the talk. Why did I start working on Backscatter radio? This is the problem. We wanted to network a greenhouse. We wanted to put very low-cost sensors, install very low-cost sensors at each plant in a greenhouse. Why? You want to monitor soil moisture in order to precisely irrigate the precise amount of water needed by each plant. You want to control environmental humidity. Why? Because if environmental humidity exceeds the limits, then you need more pesticides, more chemicals, which essentially results to more chemistry in your stomach. So, if you want to network each plant in a greenhouse, if you want to put a sensor at each plant here, you need many sensors in a greenhouse, which is very expensive with current technology. Okay, if you buy existing Zigbee radios, Bluetooth radios, you know that Xiaomi sells very nice Bluetooth sensors, soil moisture sensors that you can install in the plants in your house and monitor them with your smartphone. Okay, very nice devices, but they're very expensive. They're about $20 each. So if you want to have 10 of them, you have to pay $200. And not only that, you have to exchange batteries very often. Okay, so this is not a very scalable technology. It's an expensive technology. So we have to change the technology. And that was the idea. Here you have the conventional radio. You have a microcontroller unit that creates the bits. The bits are then fed to a filter that shapes the bits to an analog signal. Then you take that analog signal and mix it with a carrier frequency in order to transmit it using an antenna through a power amplifier. This is the typical radio that you have in your pocket in your smartphone. Okay? And you can build those things with $5 to $10 each, achieving megabits of speed at the cost of tens of milliamperes per bit. Okay, so this is existing Marconi radio technology, and as you can see, the radio chip costs in the order of $5 to $10. Okay, and you need a lot of current. This is a humongous amount of current for battery-operated devices. That's why your smartphone needs to be charged at night, right? The radio is the power-consuming part. So we said, okay, let's get rid of that. Let's create new radios that consist of just an antenna and a switch, nothing else. See here we have the schematic of a transistor. What is a transistor? What's a transistor? Switch. Switch, exactly. So, we have an antenna, we have a switch, and we have a controller unit, microcontroller unit, an MCU, that basically switches on and off that antenna. Nothing else. Okay? So, you illuminate that antenna, and information is modulated on the reflected signal that impinges on this antenna and gets reflected backscattered to a different device that picks up that reflected radio signal. You can modulate information on top of that by intelligently switching this little transistor. If you intelligently switch that little transistor, you can modulate information on the reflected signal. Okay? So you see the difference? How much energy do you need in order to switch on or off a transistor? Minuscule amount of energy, right? So we can create, with this principle, very ultra low power communication using an antenna and a switch at a cost below $1, a fraction of $1. And because of this thing is extremely low power, you can essentially harvest energy from the illuminating field, from the incoming field. So this guy not only illuminates this antenna, but also can provide the essential power that this module needs in order to operate. Okay? What's the problem with this? The problem is that you have to be extremely smart on how you process the backscattered signals in order to extract the information that was modulated by your sensor here. Okay? So that was the idea. And said, not only that, but as I said, you can use this principle not only to convey information, but also to build intelligent sensors, intelligent wireless sensors. So one of the projects that we did was to put install two electrodes at the stem of a plant, and use those electrodes, use actually the plant as a battery, as an electrolyte, as a battery. So take this voltage difference, okay, design carefully a harvesting system, and extract power from the plant. We managed to extract 1 microwatt from an avocado plant. Avocado, you know avocado, right? The scientific name of avocado is Persea americana. And why did we work on avocado? Because avocado is something that we cultivate here in Chania. It's profitable. People actually make money out of avocados. And it has a distinct characteristic. If you water avocado more than it needs, do you know what happens? If you put more water than it needs, do you know what happens? It dies. So it's important not only to irrigate avocado precisely in order to have good fruits, good produce, but also you need to avoid overwatering because it dies. So we managed to extract 1 microwatt during noon from the plant. With another 2 electrodes, we measured the voltage across the stem of the avocado. So basically, with other 2 electrodes, we amplified them. We fed them into a different device that converted voltage to a periodic signal. Essentially, this signal is, this module transforms the voltage to frequency. And this frequency, it's a periodic signal that basically turns on and off this transistor, switches on and off this transistor. So basically you can measure, you can convey that voltage using a switching signal on this transistor. You illuminate it from somewhere, you receive the backscatter signal from another device, and essentially the frequency with which we switch the transistor can be extracted, and you can understand essentially the voltage across the stem of the plant. I'm going to talk about it a little bit later. So, you can do amazing stuff with backscatter radio exactly because of the ultra low power. Let me talk about a little bit about the principle so you can understand it better. So how much time do you have? Okay. As I said, you have an illuminator that illuminates your antenna. In principle, you need 2 loads. 1 for bit 0 and 1 for bit 1. So if you want to transmit bit 0, you terminate the antenna at the first load. And you keep that termination for the duration of the bit. If you want to send a different bit 1 for example, you simply change the load. That's the principle, nothing else. Antenna and 2 loads, 1 for bit 0 and another for bit 1. You illuminate this antenna, information is scattered back, information can be conveyed essentially on the reflection coefficient between the antenna and the load. Okay? Whoever is electrical engineer here can understand that. Okay? We have something like an AC source, it's the incoming field from the antenna. You have a characteristic impedance of the antenna, and you have one of the two loads, whichever is connected to your antenna. So simple. Okay. Let's see the mathematics. The mathematics are as simple as this one. Essentially, you can view the antenna as an AC source. Okay, it's a signal source that brings a signal to your load. Okay? Let's say that you have two loads. One is open circuit, another is short circuit. So instead of putting a resistor there, I just connect the two antenna ports with a cable. This is this case, and that case is where I put the antenna, I leave the antenna open. I don't connect anything. So we know from circuits theory that you have an incoming field. Okay? This is this field. And you have a reflected field. Okay? Both cases is exactly the same. The difference is that because of the fact that here you have a short circuit, when you have a short circuit, what is the voltage difference? What is the voltage difference here when I install a cable between the two ends? What is the voltage difference? Who is electrical engineer here? What is the voltage difference when I put a cable between plus and minus? What? How much? Say it. 0? 0, right? It's 0. So you have the incoming field, you have the reflected field. So the incoming field is V plus, the reflected field is V minus, and exactly at this point, V plus plus V minus should be equal to 0, right? Which means that the V plus that basically reflects back to the environment is minus V plus, right? So the sum is equal to 0. So essentially, what is being reflected back in this case is exactly what is being impinged on the antenna with a different sign. Okay? Simple? What's the difference here? What's the voltage difference here, exactly here? I have infinite impedance, right? Because I don't connect anything. So the voltage difference that impedes here should be exactly the same as the voltage difference that gets reflected back. So here, the reflected signal has exactly the same sign with the impinged signal. See the difference? Here I have plus, here I have minus. So if you change this, if you simply change the load, you can control the sign of the reflected signal back to the environment. And how can we write that in a mathematical term? Scary mathematical term. Well, it's cosine. It's a simple cosine, right? Cosine. This is the amplitude of the cosine, this is the frequency of the cosine, and this is the phase of the cosine. In this case, I want the signal to be reflected back with the same sign with which it was impinged on the load. As opposed to this case, where I want a negative sign. So in this case I have plus, in this case I have minus, right? How can I put this sign inside the cosine? Ooh. First semester, calculus 1, right? Simply, here I can add cosine. Cosine pi plus something means minus cosine the angle, as opposed to this case where cosine pi plus something means whatever I have inside. Okay? So essentially, when my sensor changes between two loads, one is open circuit and the other is closed circuit, I essentially create at the environment a backscatter signal that has here a different phase, right? And that different phase essentially controls the amplitude exactly the same way as here. If you don't want to do maths and you want to do physics, you know immediately that this change of signs essentially is due to the reflection coefficient between the antenna and your load. The reflection coefficient is 1 in this case, and minus 1 in the other case. And you can simply write it like this. So if you are an antenna guy, you understand this. If you are a mathematics guy, electrical engineer guy, signal processing guy, you understand that. So simple. By changing just the loads, I can play with the sign of the backscatter signal, either plus or minus, which essentially, at the illuminated signal that has a frequency and a phase, I change the phase. So simple. Okay? This is the mathematics of backscatter radio. This is all you need in order to understand backscatter radio. And you can do a lot of tricks now. Okay, you can build on top of this principle. Let me show you a video. I have this guy who is the illuminator. Okay? It transmits, it emits a carrier. Okay? This carrier is being received by a device which is called spectrum analyzer. It does frequency domain analysis. So if you send a cosine at frequency Fc, basically you should see here you have the frequency axis. You will have a tone, you have a delta at the frequency of the emitting signal, right? So if this signal is 868 megahertz, the spectrum analyzer will give you a peak at exactly 868 megahertz. Is that clear? Okay. So here I have an antenna that basically, this little trick switches the antenna between two loads, open and short circuit. But does that with a periodic signal and score wave signal, 50% duty cycle, which means that 50% of the time is at one state, another 50% of the time is a different state. So you have a periodic signal with a different frequency, let's say capital F, let's say 30 kilohertz. So you switch your antenna between, this antenna is being switched between two loads, and you change that load with a frequency of 30 kilohertz. Okay? What you see here, you see the incoming field, and you see also the backscattered signal that impinges on this antenna and gets reflected back. And because of this frequency switch between the two loads at 30 kilohertz, you see another two peaks at your spectrum analyzer. One at 868 megahertz plus 30 kilohertz, and another at 168 megahertz minus 30 kilohertz. So you see another two peaks. Let me show you a video to better understand it. Okay. Oops. Yips. Sorry about that. Okay. So can you see the two peaks? I have 868 megahertz, 868 megahertz, which is basically a tone, a carrier, a cosine that I showed you before, at the frequency of 868 megahertz. So this is this peak. And I'm switching this antenna between two loads with a frequency of 30 kilohertz. So here I have two peaks, one at plus 30 kilohertz and another at minus 30 kilohertz, around that carrier tone. And you can see the two peaks here. Look at what I'm going to do. I'm going to change that switching frequency relatively to the humidity inside this glass of water. So you can see very carefully here that whenever I dip this sensor, the peaks are getting closer to the central peak. Essentially, the switching frequency is being decreased. It becomes smaller. Can you see it? It's here, and when I dip it inside, it's going to become smaller. Dip it one more time. One more time. Come on, one more time. Doesn't listen to me. Let me show you. Let me show you again. Okay, so we are here. When I dip it inside, the switching frequency is going to be decreased. It's going to be like this. See it? It came closer to that. Now I'm going to take it out. It's going to be closer to here. This is the marker. So it came here. Okay. What does that show you? Now I'm going to do it one more. It's going to be decreased. See? See? It came closer to this. Now it's going to become higher, closer to the right side. Okay. So what happens here is the following. You have a capacitor. This is a capacitor, right? Whenever you dip it inside the water has higher dielectric constant. Okay? So the capacitance increases. So you have a higher capacitor, bigger value capacitor. Bigger value capacitor means that the switching frequency of the sensor is being decreased. Okay, because I have an oscillating circuit that has an oscillation frequency relative to this, inversely proportional to this capacitance. So I change the switching frequency and I decrease the switching frequency relatively to the capacitance that I want to measure. So essentially what is happening here, I can pick up the backscattered signal, and from that change of frequencies, I can find out what was the capacitance here, essentially what was the soil moisture inside the glass. So with a very simple way, I can measure soil moisture. Okay? And with a device that consumes very few microwatts of power. So I can build essentially very cheap sensors. Okay? And here, you can see all the basic ingredients. You have the illuminator, you have the receiver of the backscatter information, and you have the antenna connected to my sensor that basically reflects the impinged signal, changing its characteristics depending on what I want to measure. Okay? What is the advantage of this technology? You can build extremely low power sensors, wireless sensors. Provided, of course, you are smart enough to replace this 6K machine with $10 machine with connect to your computer and intelligent signal processing. Okay? Where have you used this technology? Where have you been using this technology in your daily life? Does anybody have any idea? No idea? The RFID chips in the credit card. Well, actually, there you have, yeah, it's an RFID, but it's not this type of RFID. It's a little bit different. It's NFC, near-field technology, near-field sensors, but the principle is very similar to that. There, the coupling is capacitive. Here, the coupling is electromagnetic. Where else?
Meteorology.
Meteorology. Okay, where exactly?
Predicting the weather.
Predicting the weather? Are you sure? How's that? How's that working?
Because it has a relationship with humidity.
Okay, fine. Humidity sensors are used everywhere. But I'm talking about backscatter radio technology. Where else? Come on. I'm sure everybody has been in Zara's here in Kenya, right? Yeah. Haven't you noticed the big antennas at the exit doors? And the tags that they have installed in every garment, in every piece of garment? Those are a type of RFID technology. Essentially what happens is that if you exit the store without removing those tags, the antennas pick up those tags. Those tags have no batteries. They basically react to the illuminating signal from the antennas at the door. It's very similar to this principle. Not exactly the same, but very similar to that. Okay? So backscatter radio technology is a technology, well, actually, you have used it in the library with tag. If you go to the library and you carefully inspect the last page of the book, you will see a sticker that has a little antenna and a very small chip. And whenever you go and check out the book, they basically place it in a flat panel with an antenna that reads this tag very similarly to this principle. And basically, you can check out the book, right? It's a small antenna, coil antenna, with a very small chip inside, which is batteryless. It takes energy from the illuminating field. And the field comes from that panel antenna on the desk of the librarian. Okay? Every warehouse, every modern warehouse actually, inventories and keeps track of all the products using those types of technology, this type of technology using RFID, radio frequency identification tags, which work exactly this way. They have an antenna and a very small chip that reflects stuff and gets energy from the incoming field. Okay? The history behind this, you can read very interesting stories. So around the 40s, exactly after World War II, the US ambassador in Moscow received a gift from the, at that time, Soviet Union administration. It was this ornament, this coat of arms thing. So what do you see here? You see the American eagle, right? This is slightly big, it's about this size. Okay? So what was that? You see it and you see, okay, this is an ugly, decorative thing, right? Who cares? I mean, Americans are not very famous for the taste. Okay? But you see a useless decorative thing. Well, actually, it was not useless. Inside, there was a microphone, there was a hidden microphone. Okay? So when the US ambassador was speaking inside the office, you had a reverberation chamber here, and a speaker essentially, that created mechanical waves that impinged on this microphone, and the microphone was essentially a transducer, was essentially a switch. So the mechanical waves of the voice of the US ambassador were switching this microphone here. So outside the embassy there was a Soviet Union van illuminating with high frequencies RF signals this thing, right? And they were picking up the reflection of that signal modulated by the voice of the American ambassador. So essentially they were able to spy on the speech of the US ambassador. Great hack, wonderful hack. It was discovered a couple of years actually, not immediately. They found out, first of all, because they knew that something wrong was happening. Information was leaking outside the US embassy. And second, the RF signal being transmitted from the van outside the embassy could be picked up by other people several kilometers away. And actually, it was discovered by the countermeasure service of the UK embassy, not the American embassy. So this is called the Great Seal Bug, the thing, and it was the first, one of the first actually hacks, one of the first demos of backscatter radio technology. Okay, so let me show you what else can be done with this technology and some basic basic principles. So as I said, you can switch your antenna between two loads. If you keep the load connected to the antenna constant during the bit that you want to transmit, you have this type of modulation, on-off key. And here you can see time. And this is the received signal, processed signal, baseband signal at a software-defined radio in the laboratory. So you see a noisy version of the signal because there's noise there. It's not only signal, you have noise plus, you have signal plus noise. So essentially what you see an amplitude for one bit. Let's say that this is bit 1 for the duration of the bit. Here I have one bit, here I have a second bit, the same bit, so that the load remains the same, so the amplitude does not change. Here the amplitude changes because I have changed the bits, I have changed the load at which I connect my antenna, and so forth, right? This is time domain signal, this is frequency domain signal. If I do frequency analysis in this signal, what I'm going to see? I'm going to see a fundamental peak, which is the frequency of the illuminating signal, and all the information is around this peak. Okay? The second way is basically what I showed you before with the capacitor and the glass of water. I can change the connection, I can change the two loads, I can change the rate with which I connect connect my antenna between the two loads. So how do I distinguish between bit 0 and bit 1? Simply by changing the frequency with which I connect the two loads. Here I have a smaller frequency, so I switch my antenna between the two loads with a smaller frequency. Here I have a higher frequency. So I'm constantly switching between the two loads, but the frequency with which I switch depends on the bit that I want. For bit 0 I have a smaller frequency, for bit 1 I have a higher frequency. Okay? And what is interesting is that if you go here and do frequency analysis, you get all those peaks. You get the illumination signal peak, this is frequency, right? So this is the frequency of the illuminating signal, and you get another 4 peaks. This and that is the frequency, plus minus frequency that I use for bit 0, and the other pair is the plus and minus frequency with which I switch for the bit 1. As I said, I have 2 frequencies, one for bit 0 and another for bit 1. One would expect just 2 peaks in the frequency domain. No, you don't have 2 peaks, you have 4 peaks. Because you have the central frequency plus minus the switching frequency. Okay? And actually, you don't have only that. You have those frequencies, let's say 30 kilohertz. Let's say that you have 30 kilohertz for bit 0. So you have carrier frequency plus 30 kilohertz, carrier frequency minus 30 kilohertz. And you have also 35 kilohertz for bit 1. So you have carrier frequency plus 35 kilohertz, carrier frequency minus 35 kilohertz. But you also observe other peaks as well, the odd harmonics. Why? Because this signal with which I'm turning my antenna between the two loads is a pulse train with 50% duty cycle, and we know from signals and systems, if you're an electrical engineer, if you're studying electrical engineering, you know that if you have a pulse train with 50% duty cycle and fundamental frequency F0, you have all the odd harmonics. F0, 3F0, 5F0, 7F0, and so forth. So here you see the 3rd harmonic, 5th harmonic, 9th harmonic, and so forth. Okay? And they basically vanish gradually. This is extremely important if you want to create efficient receivers. If you go back and open your telecommunication handbook books that you are getting, that you study in your 6th semester, 5th semester, 6th semester, 3rd year or 4th year in our curriculum, you won't be able to extract the whole signal. You will design suboptimum receivers because traditional radio does not work this way. Okay, so you have to redesign all the communication algorithms. Essentially, since you have, if you focus only on the principal frequencies, since you have 4 peaks, you need 2 match filters for bit 0 and another 2 filters for bit 1. Exactly because you have 4 peaks. You have 4 peaks, you need 4 match filters in order to create your optimum receiver. And we managed actually to explain mathematically this phenomenon. And on top of that, we managed to build optimum receivers, not only with 6K machines, but also with $10 machines, based on software-defined radio, inexpensive software-defined radio, and smart signal processing. Okay? And if you do the analysis, I'm not going to spend too much time on that. It's not that easy as it looks, because you have the channel between the illuminator and your receiver. This is the channel. You have a channel between the illuminator and the tag. This is the channel. And you have another channel between the tag and the software-defined radio. So you have 3 channel gains. If you do the analysis in baseband, if you down convert all your signals in baseband, meaning around frequency 0, those 3 channel coefficients become 3 complex numbers that you don't know. So 3 complex numbers means 6 unknowns, right? You also know nothing about how well the tag behaves as a reflector. Okay? And of course, you need to extract tag's signal. So if you work out the mathematics, you will end up with equations, fancy-looking equations like this, for Aronoff-King or for FSK, for the 2 modulation schemes that I showed. Then you need to design your filters. As I said, you must have 2 filters for bit 0 and another 2 filters for bit 1. So there you have all the filters. Okay? And I want to emphasize that if you don't take into account the analysis and you go back to your telecommunication books for classical radio, you will lose 2 out of 4 filters, because the signal in typical radio is different than in this case. So if you implement those receivers, you will basically lose half of your signal. Okay, so we did that. We did analysis with error correction. We did analysis with schemes which are, as we call them, coherent. Signals, schemes which are non-coherent. You have to estimate all those unknowns, or you have to do detection without estimating all those unknowns. We managed to solve those problems. And to make the long story short, we realized that the schemes that we were working on for backscatter radio for plants, measuring soil moisture in an agricultural field, were exactly or very similar to underwater communication schemes used in underwater communications, for example, submarine talking to another submarine, or to satellite communications. Why? Because those 3 cases, backscatter radio, underwater, and satellite, are cases where the signal at the receiver is extremely weak. Okay? You work there at the power limited regime. So we ran into problems in backscatter radio which were very similar to the problems that we have in ultra low power, power limited regime communications, found in underwater and satellite communication that were unsolved for the last 30 years. And we managed to solve them. Okay? One of the problems was that if you want to extract information when you have very weak signals, and you don't know the channel, and you have no ways to estimate the channel, the only way to estimate the channel is from the data that you receive themselves. So you have to estimate the channel and at the same time detect your bits. There are ways to do it, but there were complex ways to do it. So we wanted to do it very quickly with low complexity. That was an open problem. We managed to solve it, both for backscatter radio as well as for the other problems. So eventually we managed to have extremely high range communications with backscatter radio. Here is a picture. Here is the illuminator. Here is the tag. So this is the garden in the science building down outside at the south part of the campus. You know, all of you know this garden, right? It's outside the coffee place of the building, the science building. So here we have the emitter, here we have the tag, and the receiver is at the end of the corridor, right? So it's about 300 meters or so. So we managed to pick up the signal, extract the information from the tag using smart signal processing and encompassing everything that we know in electrical engineering. Okay, so we have detection algorithms, we have error correction algorithms, we have electronics, we have software. This is software-defined radio, and all of them with extremely low cost. Okay, we can basically build schemes like this with very inexpensive techniques. And for that, people, of course, appreciate it. We received a bunch of awards. I'm very proud about this. The latest one, the last one is on May at Thessaloniki. This is an undergraduate student. When he did the work was summer intern in my lab at the end of his 3rd year. So he was an undergraduate. And when the paper was published in May, he was a 4th year student. Okay? The other one is here is my PhD candidate, Giorgos Voulioukas. This is Mikhail Joglou. This is Giorgos Voulioukas. He received Best Paper Award at RFID ETA at Poland 2017. And this is 2015 at Brisbane, Australia, with Professor Christinos, with Foutoulas and Alivisios, the 2 PhD students who did this work. We collaborate a lot on this project with Giorgos Christinos. And this is actually a very prestigious award. The ICASP awards are very prestigious. 2015. And others as well. Let me show you a demo. and you will understand what I'm talking about. I have prepared many slides. How much time do we have? Do we have 15 minutes? 10 minutes?
We have about seven minutes.
Okay.
So we can ask some questions.
Okay, so I'm gonna finish then. I'm gonna show you just a few pictures. So this is the very simple principle that I showed before. You have an antenna that switches between two loads with a frequency that depends on what I want to measure. What I want to measure here is environmental humidity. That was the first that we did. The second is that we replaced that capacitor for environmental humidity with a capacitor that we built for soil moisture. And this is the last one, which I'm very, very proud of. Think of an illuminator coming from the signals that you use in order to listen to music. Okay? Radio signals coming from Alexa, 6.5 kilometers away from here. So this is the illuminating signal. That signal impedes your antenna, and it's being modulated in a smart way so it can convey information about the soil moisture at the soil in a way, however, that you can pick it up from your smartphone commodity FM receiver. So your smartphone becomes a receiver of backscatter information in a way that you can essentially, literally, listen to the soil moisture of your favorite plant. Let me show you the demo. Okay? It's being powered by a lemon. So small power that you can power it from a lemon. The signal is coming from FM. You are listening to your smartphone that has FM receiver, commodity FM receiver. See, I watered and the tone changed. So from that tone, I can understand that the plant was actually watered. It's exactly the same principle as here, but instead of having your dedicated illuminator, you don't have a dedicated illuminator, you have the illuminating signal coming from Alexa. And here, instead of having a 6K machine, you have your grandmother's favorite FM receiver that cost a few bucks. Actually, no, you have a smartphone that has a FM receiver, but essentially it's the same technology. Okay. Having said that, I don't have much time, I have prepared more stuff, but I think I'm going to stop here. I want you to remember one thing. That was the plant that we managed to measure environmental conditions. That was the apparatus basically that we used in order to harvest energy from the plant, and also with another two electrodes convey that information of the plant itself, treat the plant as a sensor itself. That was something that I did with Professor Koutroulis. I want you to remember this slide. Sorry. Scatter radio is tricky. You have to be very careful when you do your signal processing. Otherwise, you will lose at least half of your signal. Because of the fact that it's extremely low power, you can power your sensors with whatever sources you can imagine, either electrodes from a plant or small solar panels, coincide smaller panels. Right? We can basically power whatever you saw up to now with solar panels that basically have a surface as small as a euro coin. Okay? Plants are sensors themselves, and you can use scatter radio to convert that signal. You can basically infer whether the plant was actually watered or not by monitoring the plant signal, voltage signal conveyed with backscatter radio. And of course, backscatter radio is a wonderful field of studies that encompasses all aspects of electrical engineering as you study them, and it's a wonderful field in order to test what you study. So, thank you very much.